Okay, Ji, Bismillah Rahman Rahim. In the previous lecture, we were discussing the Backus Nor form, and we just saw a few introductory notes regarding this. Basically, Backus Nor form and the syntax diagram is a way of representing the syntax of a language. And as we know what a syntax is basically the rules that state that relate to a programming language. Now, if we can arrange our rules in this formation, that means we can somehow program these rules in at the time of creating a compiler for a particular programming language. And this is essence, this in is a way of how we represent your syntax for a particular programming language. So first step is to arrange the rules for ourselves. We should be able to understand what the rules are, and BNF and syntax diagram as well provides us with a set of techniques that allow us to formulate the set of rules for a particular programming language. Now, the basics of your your syntax diagram versus your Backus-Naur form were that your syntax diagram again consists of, these are known as the non-terminals, and if it's in the circular form, that would be regarded as a terminal. And as opposed to your Backus-Naur form, your non-terminals are represented using this symbol around the chosen identifier or the word you have chosen as the rule defining word, the term that you're defining here. So if it's a non-terminal, you will place these two symbols around that word. And if it's a terminal, you don't have to use any of those symbols for that representation. Similarly, as you can see here, these arrows are used to represent the basic flow of what this rule is trying to create. So basically, this is the rule for defining an identifier. And this rule states that first, there should be a letter. And afterwards, you can have any sequence of letters and digits, any sequence. And if you follow these arrows, you will be completing, and you follow in such a way that you exit properly. That means you have satisfied the rules for defining an identifier. So a similar technique is used for Backus-Naur form as well. Now let's look at a little more details regarding the rules defined in this Backus-Naur form, and then we will look at an example from a past paper question from your A-levels Cambridge exam and see how that particular problem is to be solved when it comes in your exam. Now, let's look at this example first. In this representation of a Backus-Naur form, you can see, as mentioned before, these are non-terminals, and this symbol here means defined as. Is defined as. Now, what this means is that identifier can be defined as a letter. As you can see here, letter itself is a non-terminal, which means that there should be a further definition of what a letter exactly is, because it's a non-terminal. If it was a terminal, it would no longer require any further definition. That value is to be treated as it is. But since it is a non-terminal, we have to elaborate on what that value really is. So if it is a terminal, non-terminal, which it is, there has to be a definition somewhere. So a letter is what, sorry, an identifier is what is defined by a letter or an identifier followed by a letter or identifier followed by a digit. Now I've got three options here. So this bar is read as or. So it's basically separating the three options that I'm giving to the terms that can be regarded as an identifier. Now let's try to understand what's happening here. Now imagine that I have a statement in something like statement that is written something like this. So let's say we have an identifier by the name of sum1 1, 2, 3. Now, according to this rule and according to the general perception of identifiers, it is actually it's a perfectly valid identifier. And how do we know this? Because this identifier will be satisfying this rule right here, this multiple of these rules. Okay, now let's try to understand how this term satisfies the rule of being an identifier. Okay, so let's see how a compiler will analyze this term here right now. So it will start with just one letter at a time. So according to this, it will start with this first letter. Now, according to this first part of my rule, it says that if it's just a letter, and what is a letter? Letter can be either uppercase or lowercase. Okay, so if it's an uppercase, then uppercase letters can be any one of these letters. As you can see here, uppercase letters can be chosen from any one of these terminals. As you can see here, there's no symbol for non-terminals here. So there's no further definition. So S is just an S. There's no further definition. There's no further, options of S. S is to be treated as it is. So since S is an uppercase letter and an uppercase letter is considered as a letter, and my identifier states that it can be just a letter to be considered as an identifier. So that means this S is actually an identifier. Okay, so we've established that S is an identifier because we followed the letter rule, the definition of what a letter is, then we followed the definition of what an uppercase letter is, then we followed the definition of uppercase letter to lead us to the fact that S is in fact a letter, an uppercase letter, which is a letter and which is an identifier. Okay, now let's look at the second part. Look at S and U. Now we just established that S is an identifier, no doubt. We just established that by our sequence of rules, we established this. Now after that, there is S and U, which means that there is another letter following my S, which I have just established as an identifier. So by this logic, can I have a letter after identifier? Is there any such option in my identifier rule that states that if there is a letter after an identifier, it will also be considered as an identifier? Yes, in fact, we do have a we do have a rule like this. If you look at this rule, it says if an identifier is followed by a letter, then that too is considered as an identifier. So that means, and again, let's follow through what a letter can be. Letter can be an uppercase or lowercase, since U looks like a lowercase. Let's look what lowercase is. Does lowercase have U in it? Yes. So yes, U is a lowercase letter. A lowercase letter is a letter, and identifier can be followed by a letter, because of which SU is considered as an identifier. Now, since I've just identified SU as an identifier, so can an identifier followed by a letter? Yes, this rule applies again, and because of which SU followed by M will also be considered as an identifier. Since I just established that SU is an identifier, and this rule states that any letter that comes after the identifier is also an identifier, that means SUM will be considered now as an identifier. Okay, so SUM is a perfectly valid identifier, but our proposed identifier does not end here. It has a number after it as well. So do I have any rule that states that if there is a digit after the identifier, it will also be considered as an identifier? Yes, we do. We have this rule over here. We have another option for the identifiers that says that if there is a digit after the identifier, that too will be considered as an identifier. So am I satisfying this rule over here? I just established that SUM is a perfectly valid identifier. And if an identifier is followed by a digit, now is 1 a digit, by the way? So let's look at what 1 is a digit. Yes, 1 is a digit, and digit has the definition of digit has this sequence of terminals in it. Is 1 in it? Yes, there is. So that means 1 is a valid digit, and since this one is a valid digit and identifier can be followed by a digit, that means sum one is a perfectly valid identifier. Since sum one is established by as an identifier, it can have a digit after it because of this rule. Now sum one two is again finalized as an identifier, and followed by this, there's another three here, because of which again this rule is going to be used, because of which now sum one two three is considered completely as an identifier. So what that means is that my proposed identifier sum 123 according to this language, according to this syntax for this particular language, is a perfectly valid identifier because I have traced all rules, and this particular term satisfies the rules for an identifier. So this is how you treat, this is how your basically compiler is going to be treating each term based on these rules. If it's an identifier, compiler will actually check according to these rules, does this identifier which you state as an identifier satisfies the rules of this language of being considered as an identifier. So in this case, it does. So in that case, my compiler will not generate an error for this. If, say, for example, I have used a character like this, and 1 2 followed by at the rate. Now it says that identifier 1 2 sum 1 2 is a perfectly valid identifier, and some identifier can be followed either by a letter or a digit. Now this character is not a letter because none of the uppercase or lowercase letters has this term in their definition. Neither is this at the rate symbol a digit because none of the digit definitions has this symbol in their definition. So that means my compiler will generate an error because it does not identify this thing as neither a digit nor a letter. In which case, this is not a valid identifier because it has not satisfied any one of these rules. So this is basically how a compiler or language translator will be analyzing a syntax written for a particular language. So this is just one example. Now, let's move on to another example. Now, as you can see here, the aspect of loop is a sort of a loop allowing for any length of letters or any length of letters and digits, or in fact, any length of characters in an identifier has been introduced in this case. Now, in this particular example, I chose sum 1, 2, 3. I can have chosen any length of characters, and as long as they are either valid digits or valid digits or valid letters, it does not matter how long the identifier is because there is no specification of that. So there is a loop. There's a sort of any length of characters in an identifier allowed loop. So, and this is how it's interpreted with respect to your language translator. Okay, now let's try to understand this example over here. Now I have got a syntax diagram that states what an unsigned number can be. So an unsigned number, as we know that there's no positive negative mentioned here, so that's considered as an unsigned number. An unsigned number it should be following this rule with respect to your syntax diagram. And what it states is this. Now let's try to understand what this means. An unsigned number is an unsigned number if it has to start with an unsigned integer. So what it is an unsigned integer? Obviously, there has to be a definition of what is considered as an unsigned integer because this here is a non-terminal. So an unsigned number has to start with an unsigned integer followed by this decimal point. Now, the reason that this decimal point is written in a circle is because this decimal point is here a terminal. So that means that there is no other option other than to enter a decimal place here. There is no options here. This is the final value that's supposed to be entered. And in a way, if you, for example, just for one moment, ignore this line over here. This means that unsigned integer followed by a decimal place. And this decimal point character has to be written in this exact way after the unsigned integer. And it has to look like this as well. It should be a decimal point because this is here is a terminal. There is no other option. There are no alternatives for what is supposed to come here. It has to be a decimal point. And followed by the decimal point, I have to have another unsigned integer. Now, let's see what's happening here with respect to this path over here. So basically what this means is that an unsigned number can have an unsigned integer followed by a decimal point and followed by an unsigned integer as it is. So what that means is that if you are writing a real number, that real number has to have an unsigned integer, and the real number, as expected, the real number has a decimal point in it. It has to have that decimal point followed by another unsigned integer always. So if you are writing a real number, this is the path, this is the sequence of characters that are mentioned in my syntax diagram. On the other hand, if you focus on this path over here, now I'm actually giving you options. Now what this means is that you may choose not to write a real number. And if you don't write a real number, that does not mean that that number is not an unsigned number. It's still an unsigned number because this rule states that my unsigned number can either be a real number or it cannot be a real number. It doesn't have to have a decimal place in it. So as you can see here, if I take this alternate path and I'm writing an unsigned integer, and it's not a real number, by the way. So after writing one unsigned integer, I can skip the decimal portion and completely end my diagram here. So that means if I choose not to write a decimal place, that will still be considered as an unsigned number. Now, one thing to remember here is that in the terms of syntax diagrams, I have to be able to reach this ending point of the diagram to be considered to have satisfied the rules defined here. So if I choose not to say add a decimal place, I can take this path and reach the end of this diagram. Now, if, for example, I did not mention this alternate path, that means that I have to have a real number. In which case, if I have chosen not to write a real number and my unsigned number syntax diagram does not have this alternate path in it, that means I will not reach this end position because my number does not have a decimal place in it. And that's how I know that that particular number does not satisfy the rule for unsigned number. So again, this is basically, if I were to represent this as Backus-Naur form, this would mean my OR symbol. This represents my OR symbol. That straight bar we were talking about, this is my OR symbol. Now we'll be looking into that in a bit, okay? Now, there's another rule because as you remember, unsigned integer is a non-terminal. So if it was a Backus-Naur form representation, that unsigned integer would have its own representation of what an unsigned integer is. It would have its own definition. But since we're working on syntax diagram right now, what a non-terminal means is that it should have its own syntax diagram. So anytime you have a non-terminal, a rectangular shape used in a syntax diagram, that means that it should have its own syntax diagram separately just to define what it is. So this unsigned integer, since it is in non-terminal, that means there should be a syntax diagram stating what a non-terminal is. Now that's exactly what this thing is. So what is an unsigned integer? Unsigned integer can be a digit. Now, as you can see here, there is a loop. There looks like a loop here. So that digit can be of either one only, it could be length 1 as well, or it could be of any length as well. Now let's look at how this loop actually works. So if I have chosen a digit, say, for example, I've chosen a digit like I've chosen this digit right here, 357. Now, let's assume that 3 is a valid digit. Yes. Is it a valid digit? Yes, 3. Does my syntax diagram allow for more digits? Yes, it is. So after reading the first three, can I come back to read the five? Yes, I can. Can I, after reading the five, can I come back to read seven? Yes, it is. So that means this sort of loop structure, it is actually a loop, allows for a digit of any length. So whenever you see a loop here, we saw this example ahead as well, before as well. As you can see here, this is also a loop structure. I'm coming back for more, I'm coming back for more letters or digits. So whenever we see such a loop structure, that basically means what? That I'm introducing a length of any length of characters here. In this case, any length of digits here. Okay, so again, this means any length of digits, any length of digits. Okay, since you can see that digit is also represented with a rectangle. So what that means is that this digit is also a non-terminal. So that means it too should have its own syntax diagram. And that's exactly what this is over here. So this is the definition for a digit. Okay, so what is a digit? Now, as you can see here, this has a sequence of terminals mentioned in it. So that means if I choose any one of these options here, these options require no further definition. They are as it is to be treated just like this. So if it's a 7, it's just a 7. There's no other option. 7 looks any differently. No, it's just this exact same representation. So these are all terminals. So if it is a digit, how do we know it's a digit? Digit can be either 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. So if I've, for example, chosen a digit to be 5 at one point, one digit is it 5. So can I take 5 as a path? I start from here, I take this path, and I reach the end. So that means since I reached the end here, following this, I've started here and I somehow made it to the end. There's a path for me to go from the start to the end. That means the value that I chose is actually a valid value. Same thing goes with 6. If I start here and now go from 6 to the end, so that means if I reach here, that means 6 is also a valid value. But now here's the interesting part. These alternate paths, as mentioned before, these are represented as an or an option in your Backus-Moore form. So at one time, digit can be either 1, 2, 3, 4, 5, 6, 7, 8, or 9. So at one time, it can hold only one of these values. So now let's look at the Backus-Moore form representations for these three syntax diagrams. Let's look at the unsigned number first. As mentioned before, the unsigned number, and this is the defined by symbol. So it has been established that for an unsigned number, you can either have a whole number, unsigned integer as a whole number, or it could be an unsigned as a real number, in which case you have an unsigned integer followed by another unsigned integer, just one unsigned integer. Okay. Now, these three lines are written in separate, these three statements are written in separate lines. That's not important. You don't have to write it in separate lines. You can write this right next to over here, like we did over here. You can write it in the same line. That's all right. Because this is the marking screen screenshot, they have separated the marks and line wise. So that's why they've written in separate lines, but you don't have to write it in separate lines. You have to write it in the same line. Anyway, so unsigned number is defined by either, you see, either as just a single unsigned integer, either as a single unsigned integer, read that and end this diagram, or it could be an unsigned integer followed by a decimal place and then another unsigned integer. So notice that I have nothing written around the decimal place. There's no symbol used for the decimal place here because this is the Backus-Moore form. And decimal place, this decimal point symbol is actually a terminal. It has to be written in exactly this way. There's no further definition of this. However, what an unsigned integer is, it's actually a non-terminal. That's why it's written in this way. Same thing goes with this representation as well. So that means there has to be a Backus-Moore form representation for what an unsigned integer is. And this is exactly what it is. Now, unsigned integer is a digit or it could be a digit unsigned integer. Now, this is an alternate answer, right? This is an alternate answer. And actually this answer makes more sense. I'll explain why. So we're going to be using this form. Unsigned integer is what? It is a digit, a single digit, or it could be an unsigned integer followed by a digit. Now let's check this out. Why did this? Okay, it makes sense that unsigned integer can be a single digit. Okay, and that's no problem at all. And again, what is a digit? Digit is defined by either 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. As you can see here, I have no marks for a non-terminal here because these characters are supposed to be written as they are in the form of terminals. Okay, now let's go back to this representation over here. Now, let's say I have this number here. Again, let's go back to 357 as an example. I can just, okay. 357 as an example. Now, obviously, this part, this is a it could be of any length. And my rule states that it could be of any length. Again, we are using this representation. You can ignore this whole part. This is the right answer. This is right as also, but this answer somehow makes more sense. Okay. Now let's look again. The same rule applies. That is this an unsigned integer? Let's start reading this. Is 3 a digit? So my compiler will start analyzing the first character on the left and see, is 3 a digit? So is it a digit? According to this rule, it says that if it's only a digit, then it's an unsigned integer. But is it really a digit? Does digit have 3 in it? Yes, 3 is part of the digit. So that means since this is a digit, then this alone 3 is a perfectly valid unsigned integer. Okay, so that means, okay, 3 is an unsigned integer. But my second part of the rule, the second option states that an unsigned integer can be followed by a digit. I just established that 3 is an unsigned integer because it satisfies this part of the rule. It is a digit and the digit definition has 3 in it. And since this is an unsigned integer, my second part of the rule says that there can be a digit after the unsigned integer. In which case, unsigned integer, which 3 has just been established, is followed by a digit, which I think 5 should be a digit. Is 5 a digit? Does digit have the digit definition have 5 in it? Yes, it does. So that means if an unsigned integer is followed by a digit, it will also be considered as an unsigned integer. So that means 3 and 5 are now our unsigned integer. So according to this rule again, since this is an unsigned integer, followed by another digit should mean that this too is an unsigned integer. And by the way, 7 is a perfectly valid digit. So that means unsigned integer followed by a digit, 35 followed by 7 is actually an unsigned integer. So that by this rule, my 357 is a perfectly valid unsigned integer. And this is how a loop of n, and now as you can see here, I can grow this number to any number of digits, and I will keep on using this rule to consider them. As long as they're valid digits, I will keep on coming back to this rule and calling them an assigned integer. So this allows an option for entering any length of characters, any length of numbers for source. And this can be used for letters as well, as we saw here, as you can saw for digits. So whenever there's an aspect of loop, we're going to be using this method of writing the Backus-Moore form.